So let's start with the topic of today, which is slope stability. So as I mentioned, I will start with a short presentation to give you some general information about slope stability. I'm not going to dive in too deep into the theory. I just keep it general and relatively simple so that we are all clear with the basics. So what is a common definition of a slope? A slope is an inclined surface of soil or rock, which is capable of suffering failure or performance loss. We can categorize them in two big categories, let's say. The natural slopes, like valleys, hills, or coastal cliffs, and the man-made slopes, so the artificial one, such as excavation, embankment, or earth dam. You can see a few examples on my screen. Regarding the failure mechanism of slope, we can distinguish four big failure modes, let's say. The rotational slip, so basically the slope follow a kind of curve and slide along this curve. The translational slip, where the slope follow a rectilinear, a longitudinal line and slide along this line. The flow failure, which is depicted on this sketch, and also the wedge failure is one of the most known failure mode. The causes of slope failure can be based on one of the causes can be the slope type, the inclination of the slope. The loads can be one of the main causes. An excessive pore water pressure also, or loss of shear strength due to seepage or liquefaction. So these are the common causes of slope failure. Now let's talk about slope stability analysis. So the purpose of the slope stability is to determine whether a slope of soil is safe or not by means of a factor of safety. What is the factor of safety? The factor of safety is basically the ratio between the maximum load that soil can sustain, let's say the maximum shear stress, and divided by the actual load or stress that is applied, so the actual shear stress, basically. And this ratio determines if a slope is safe or not. So if the factor of safety should actually be higher than 1. If it's not higher than 1, then your slope is definitely not safe. We can distinguish two approaches to slope stability analysis: the so-called limit equilibrium methods and the finite element method. The first one is available only in 2D. It consists of several methods. Most of them, the most popular are Bishop, Spencer, Jambu, but there are many of them. In the limit equilibrium method, the soil mass is divided in slices, and assumptions are made to satisfy equilibrium, and most likely failure mechanism is determined. For finite element method, 2D and 3D cases are considered, so it doesn't matter. The equilibrium is obtained by continuum mechanics. There's no restriction regarding the geometries or the heterogeneities that can be considered. You don't need to make arbitrary assumption for the shape of the failure surface. Various elastoplastic soil models can be considered, and both factor of safety and failure behavior are determined. In this table, I try to summarize differences between these two approaches in terms of equilibrium, stresses, deformation, failure and kinematics. So you can see that finite element method has some strong advantage. So within the finite element approach, we can highlight two methods. The increase of the applied load. So in that case, all the material properties are kept constant. The load is increased until loss of stability, and the failure mechanism and the ultimate load are determined. Another one is the reduction of the strength characteristic of the soil, also called the CFE reduction method. The self-weight and additional loads are applied at their nominal value. The strength characteristic of the soils are reduced until loss of stability. The failure mechanism and the safety factor on material property are determined. So when you compare both methods, the strength reduction method is preferred. The uncertainty is usually larger on material properties than on applied loads. So the SRM method is definitely a must. Now, if we look at the factor of safety in geotechnical engineering, it's basically the ratio between the nominal shear capacity and the reduced shear capacity causing failure. And it should be larger than 1 for safety. When you use the strength reduction factor in the CFE reduction method, basically the cohesion and the phi are reduced by this strength reduction factor until an equilibrium is reached. You can see the scale down of this phi C. So let's have a deeper look at the strength reduction procedure in Diana. So in a strength reduction analysis, first the self-weight and additional loads are applied on the structure using a standard phased or non-phased nonlinear static analysis, and an equilibrium state is obtained. Next, the module or the strength reduction module is run to determine the factor of safety. At each iteration of this process, nonlinear analysis is carried out. So on this schema, you can see the iterative procedure for the factor of safety. We basically increment it with a delta Fs, which is user input. First we start with a factor of safety, which is user specified, but by default it's 1. We increment it with a delta Fs, which is also user input. And by default, Diana takes 0.1. Using this new incremented safety factor, we scale down the cohesion and the friction angle. Then with this reduced parameter, we perform a nonlinear analysis and we check if we get convergence or not. So if we get convergence, then we increment again the safety factor with delta Fs. If not, we reduce our delta and we divide it by 2 and compute a new safety factor, and again perform a nonlinear analysis until an equilibrium is reached. So this is the iterative process which is used in Diana. Presently in Diana, only the more Coulomb and Drucker program model, as well as the Coulomb friction for interface elements, are considered. The strength reduction analysis must be preceded by a standard nonlinear static analysis, as I mentioned. You apply your self-weight and any additional loads, and then you activate, you run the strength reduction. The user do not need to specify any load case in the strength reduction. And the main output of this analysis is, of course, the factor of safety, which is really the main output of this analysis. So this is it for this short presentation. Now let's go to the live demo. Before I start the live demo, I would like to give a little insight on the model we are going to use today. So here is a sketch of the soil. So the model consists of a soil domain with a base of 80 meter width, a height of 20 on one side and 30 meter on the other side. And the soil surface has a gentle slope in the middle. For the material behavior of the soil, we assume a Moore-Coulomb model with parameters that are listed here. And the goal of today's slope stability analysis is to perform a slope stability analysis, and compare the resulting factor of safety with other programs. So this case studies is coming from a reference paper from a master thesis by Nermin Albatanei from University of Ohio. So there is a reference, and in his thesis he compared different software. So we know already that for this slope stability we should expect a factor of safety of 171. So let's see what Diana give for this case. So now let's move on to the live demo. So I'm going to start Diana. So I will quickly go through the Diana interactive environment for those who are new to Diana. So this is how it looks basically. It's quite Windows oriented, as you can see, with tab on the top, and you have a different window on the side. So this main window is your working window on the left, but you can also move them to the right. I mean, it's very flexible. You can find the geometry tree, the mesh tree, the property tree, and you can add more from your window option. You can add some model selection item, toolbar, window span. You have also the analysis and results environment here. You have the action panel on the right with all the action that are available in Diana. And at the bottom, you can see that you have two boxes, the message box, which usually displays some analysis output or any message when something is going wrong, and the command console. The command console is very interesting because the Diana GUI make full usage of Python. So it means that everything you click or you do in the interactive environment is scripted in Python. So all the command can be echoed in this command console, but it's also saved automatically in a file, a kind of history file that you can find on your computer under your user directory. You will find a Diana IE folder which contain all the history file that you have created. For your information, an history file is, or a Python script file, is started when you start a Diana session, and it's closed when you close the Diana session. So all the actions that are done between the start and the end of the session are saved in this Python script. So it can be very convenient in case the program crash, or you want to change something. You can replace the Python command at any time. You can change them. You can also include the loops or program if you like developing Python code. So this is one of the nice features of interactive environment. But I'm not going to say more about that. I'm just going to start my model. So when you start a model in Diana, first you need to define a new project. So you go to the file, new, and here you have the new project window. So you need to specify a project name. So I'm going to call it slope demo. You can browse to your working directory. I have an e-learning slope stability folder for that. Next, you need to specify the analysis type. This is important because this will narrow down the choices in terms of loads, element types, and so on that you will have available in the GUI. So by picking up the right analysis types, and we narrow down the choice to limit the source of mistakes, let's say. So today we are going to perform a structural analysis. We are going to model plane strain. And for the model size, I just keep the default, but I want to say a little word on that. This model size is an important point, or let's say an attention point, because it really determines the size of your modeling box. So you can see that using a model size of 1 kilometer, I basically create a modeling box of where the limit or the diagonal goes from 500, 500, 500 to minus 500, 500, 500. So it's the external dimension of your box, which is centered on 0.000 basically. So make sure that the model fit in this box. So this dimension is quite important. So today I choose for a size of 1 kilometer, which is definitely big enough since our model is 80 meter long and 30 meter high. For the default measure type, I'm going to choose for hexa quad dominant. You have the option between tetra or triangle dominant element or hexa quad element. And I will keep the mesh shoulder as linear. So once you have filled in all this field, you can click OK. And you can see in the command console that this action results in a set of Python command line, which basically gives the information I entered in the dialog box. So the dimension, 1000 meters, the structural analysis type, plane strain dimension, mesh order linear, mesh type hexaquad, and also the path and the name of my project. Next thing now is to check our unit system. We choose SI units, so you can find the units on the right bottom corner if you click there. So today we are going to use meter, kilogram, Newton, second, Kelvin, radian. Be aware that this is, you can change the unit at any time and it automatically updates and scale up the value that you have already entered. So it's very interactive. For the angle, I'm not going to use radian, actually I'm going to use degree since our material property, the friction angle is, and the cohesion are and the latency angle, are specified in degree. I will use degree to facilitate the input. So now let's start the modeling. I quickly go back to my presentation. So this is a sketch of the model. And what I'm going to model is basically this soil domain. And to do that, I'm just going to use the point coordinate of this 8 point. 1, 2, 3, 4, 5, 6, 7, and 8. To save time, I have already entered this coordinate in an Excel sheet, so I will just need to copy paste. So the first action is to add a polygon sheet. So I click on the add polygon sheet icon. I'm going to call it soil 2D. And for the method, I'm going to choose the coordinate. You see that we have three options: rectangle, coordinates, and relative coordinate. And today I'm going to use coordinates, so I just need to specify all the point coordinate that describe my polygon sheet. So for that, I have an Excel sheet here where the coordinate of my 8 points are listed there. So I just copy and I paste them here. And if I zoom out, you can see already a preview of the shape. But wait, because the shape is not created yet, I need to click on the Create button. This is an important attention point. You define your polygon sheet, you give it a name, you enter your input, but until and unless you click the Create button, nothing is created. So now I create the surface. And if I go back, or I go to the left, to the geometry tree, under shape, now I can see that I have an entity called Soil2D, which is created, and which is represent my soil domain. Next to that, we are going to create the curve, which is depicted here. For this type of slope, we can expect a rotational slide failure mechanism. So basically it will slide along this curve. So we are going to model this line so that the mesh will also adapt around this curve. So to do that, we need to define a curve. So I'm going to add a curve. I'm going to name it curve 1. This is fine. Same story. I have already the point coordinate. So I'm just copy, paste. So you can see that. And again, I need to create. And then you can see that the curve 1 appears now under the shape. So I have my Soil2D and my curve. Now what I want is to imprint this curve line into my model, so that later on when I mesh, it's taken into account. So to do that, I'm going to click on this button, the shape projection. So the target type will be shape. So the shape will be the Soil2D, and the tool will be the curve. And I'm going to project that on the -z direction, so on top of the Soil2D, and I do imprint, and you will see that the curve 1 is going to disappear from my shape, but it's now part of the Soil2D. Okay, so this is it for the geometrical part. Now we are going to assign property. So whether you have the freedom to work in terms of workflow. Usually we define the geometry, whether we start by defining the properties or the boundary condition and loads. Today I've decided to start with the assignment of the property. The main thing to keep in mind is everything is done at the geometry level. So assigning material property, physical property, loads, boundary condition, all these things are done at the geometry. So every time you do any change on your model, it's done at the geometry level. It means that it will need to remesh to be taken into account in your finite element model. So I'm going to assign the property, and for that I click on the property assignment button. So I'm going to assign that to the Soil2D. For the element class, I go for regular plane strain. I'm going to define the material. So I'm going to call it Soil2D. I want to take into account the class. So the class will be soil and rock. I don't need the initial stress. I want to take into account the strength reduction. And for the material model, I choose more Coulomb and Drucker prior plasticity. So now I need to fill in the linear material property and also the more Coulomb and Drucker prior plasticity. So for the Young's modulus, let me quickly check the value. So it will be 1 in 9. Newton per square meter. Poisson ratio, we go for 0.3. We use a saturated density of 1073. For the more Coulomb and Drucker prior plasticity, we use a cohesion of 15,000 and friction angle of 20. So 15,000, 20, 0. And no tangent cutoff. So this is it for material input. So we have selected our shape, we have defined material, we have selected an element class. Now we click on create. This is important. Always keep in mind that until and unless you click the create button, nothing is taken into account. So now I click on create. So we have assigned our property. Now let's move on and set up some boundary condition. So I click on the support button. So I'm going to start with the support along the constraint in X direction, so BCX. I will create a main support set that I call BC. And I want to assign that along the edge, so I select both right and left edges, and I'm going to constrain the X direction. But I'm also going to constrain the X direction at the bottom. I click on create. Next to that, I'm going to constrain in Y, and in Y I'm going to constrain the bottom direction. Up. And I click apply, create. This is it. So we have created our lateral and bottom support. In terms of loads, we are only going to consider the self-weight. So we click on the global load definition button. So I create self-weight. Give it the same load case name, and I click create. And now if you go to the load, you can see that I have one case, which is a self-weight, and also under support you can see that I have my BC set, which consists of 2 support in X and Y. So you can always refer to what you have created on your geometry under the geometry tree. You can see that your shape appear here under the geometry. You can find back your material. You can actually edit the material if you want. You can see your support. You can see your load. So everything can be found under this tree. So we are pretty much done. We have defined our geometry, we have assigned our property, we have defined boundary condition and the self-weight. So we are going to mesh this model. So I go to the mesh seeding. So I select the target type, it's going to be a shape. For the seeding method, I'm going to specify an element size. So I select my model, and I'm going to use a 0.8 element size. You can click on preview, so you already see the orientation of the line and also the mesh seeding, and you click apply. And then finally, you click on the generate mesh button. So you can see that having this imprinted curve line, you have a nicely curved mesh along this curve. So it was the purpose. I would like to say a few words on the meshing. For this type of analysis, for slope stability analysis, the mesh density is kind of critical factor. Today I'm using a 0.8 meter element size, but I'm not coming out of blue with this value. I did a couple of trials to come to a kind of well-balanced mesh who give a good safety factor. But I strongly invite you after this session to practice a little bit with the same model and to see the influence of using different mesh size on your safety factor. This is very sensitive. And this is also highlighted in the thesis from which this case is coming from. So we have done all the modeling part. Now we can focus on setting our slope stability analysis. So for that, I go to the analysis window and I'm going to add an analysis and I'm going to name it slope stability. So this slope stability, as I mentioned in my presentation in introduction, should consist of a structural nonlinear analysis where we applied the self-wear or any additional load to come to an equilibrium state. Then it should be followed by a strength reduction analysis where we will reduce during an iterative process the C cohesion and the phi and perform for each iteration a nonlinear analysis until equilibrium is reached. So it means that I add a structural nonlinear. For this structural nonlinear, I just want to perform a start step. So I'm going to remove this one and add a start step. But I'm going to call like this. In this start step, I'm going to initial stress, which I will calculate from my self-weight. And for the additional load, I use my self-weight and one step. Regarding the iterative method, I'm going to use the sequent Casey-Newton, and I'm going to put 50 iteration, and I will only check the force norm. So this is the setting of structural nonlinear. Now I'm going to add my strength reduction. Here we go. So for the factor of safety, the initial factor of safety, if I quickly go back to my presentation, yeah, this one, the initial factor of safety, if it is this FS0, so it's 1 by default. We keep basically, I'm just going to use the default, I'm not going to change that. And the safety factor of safety increment, so our delta is 0.1. So we keep this as it is. And for the equilibrium process, we use second and also only check on the force, and here I put 200. For the output result of the strength reduction, I'm going to make some selection. So I choose a displacement, and I'm also going to add the principal strain. So from strain, total, green, principal. And this is it. So we have set up our model, and we have now set up the slope stability analysis. So first a structural nonlinear, then a strength reduction method, where an iterative process is used to reduce the strength parameter, and at every iteration a nonlinear analysis is performed. So I'm going to run this analysis, but this one will take 2 or 3 minutes, but I can start it. So you can see from the message box that you get some extra information about the convergence, and also the safety factor will appear here. I'm not going to wait until the end. I have already run the same analysis. Here we go. So if I go to the message at the end of my analysis, I'm going to increase that a little bit. So you, as I mentioned, you can see every iteration and check on the force criteria to see if a convergence is achieved or not. And finally, you see the main output of this analysis, which is final factor of safety. And with this mesh density, we reach a factor of safety of 1.71250. So let's say 1.71, which is a pretty good agreement with the other program, because as I mentioned in introduction, for this problem, a factor of safety of 1.7, 1.71 is found by other program available on the market who can perform this type of analysis. So this is the main output of this analysis. And now if I look, for instance, as a principal strain, as depicted here, for my last step, so the one where my safety factor is achieved, I can see the pattern of the failure mechanism. This is nicely depicted on this picture. I can also look at the control plot of the displacement, also show that this is going to slide basically along a curved line. So as mentioned in introduction in the presentation, both the failure mechanism and the safety factor can be determined using this strength reduction method in Diana. So you kill one bird with you kill two birds with one stone. That's the big advantage. So this is it for this live demo and first e-learning session of 2020. If you have any question, you can write them using the chat box, which is available. For those who don't have any question, who are going to leave, I want to thank you for attending this webinar.